So the hook for today is a proposal that we will put people in rockets, shoot them out into deep space, and cause them to lose weight. And the question is that reasonable? Would it really work? And I'll take you off the hook right away. The question all hinges on, what does it mean to lose weight? What do we mean by weight? And that is the first of your special forces that we are going to learn about. And what we mean by weight is the force due to gravity, how hard the earth pulls on you. Contrast that with mass, which is not a force at all, but it turns out that the amount of weight that you have is proportional to your mass. It turns out, we will learn in December, that it's also inversely proportional to the distance separating you from the Earth. And so it is indeed the case that if we were to go far away from all massive objects into deep space, that the gravitational force would fall to zero and you would lose weight. The people that we're selling this to probably want to change their bodies. They want to have their less stuff making up their bodies, that in fact they want to have their mass be different. They want their butt to be smaller. But that's not going to be what happens. That you will lose weight, but you will not do what people want to do when they try to do weight loss, which is to have less stuff making up their bodies. Okay. So that's weight. The next force that we deal with is a force that is a reaction force when you push on a surface, you push on a table. And what you are trying to do is to put your hand through the table. And there are forces, electrical forces, holding the molecules of the table together. And they say, no, we're not going to move apart so that your hand can go through here. And so because of those electrical forces, the table pushes back. And when it pushes back perpendicular to the surface. And in mathematics, when you have something that is perpendicular to the surface, we say it is normal. So that reaction force from the surface that acts perpendicular to the surface is the normal force. And it's equal to how hard you pushed yourself into the surface. That's the normal force it pushes back with. Next, I want to consider that you have a surface, say a rope, and you are pulling on the rope. Same sort of, let's see if I can make this, yeah, that's lovely. You're pulling on the rope, and again, just like when you try to put your hand through the table, what you're trying to do is to take these atoms and stretch them apart. But there are electrical forces holding them in configuration with one another, and those electrical forces say, no, we don't want you to pull us apart. And so there is a reaction force. And the name we give to that reaction force is is tension. It is indeed tension. You go away, please. Who are you talking to, Mr. Houghton? Doesn't matter. So when you pull on the rope, and you get this reaction force from the rope pulling back saying, no, you're not going to rip us apart. That force within the rope is called tension. And there is also tension at the other end of the rope, because it's not going to be ripped apart if the other end is not anchored, tied onto a wall or something. And the tension force then, compression. It acts inwards at both ends, opposing the stretch. And in fact, here within the rope, your pull on it here has created a force between those molecules, and they're trying to pull apart, and there's a tension force within the rope that avoids it coming apart. So that tension force we say it acts inwards. It is the same throughout the rope. The next force that we want to deal with is like if you have a rod and you push inward on the rod, then that creates what we call a compression. That I exert a force on the rod to try to squish it. And again, you're rearranging the molecules. You're trying to make them closer together than they would like to be. And the molecules then respond to that by pushing back. They say, no, you are not going to squish us tighter together. And so you get this, I like that without any mess up. I did it. You get this thing called a compression force. We say that it acts at both ends of the rod outward, whereas here it acts at both ends inward. A compression acts outward at both ends, and again it is a reaction force. So that's 4 special forces: weight, normal, tension, and compression. The next is a term. It is not a special force. It's about a relationship between forces. It's called equilibrium. It means you have several forces and they're sort of equaling out. What it really means is that they're adding up to 0, that they are balanced, that the net force, they add up to 0, which means there is no acceleration. And whenever you have a situation where there is no acceleration, there must be no net force. That means the forces are in equilibrium. So there's some more vocabulary. Here is a problem for you to do, and it has to do with this force down due to all these people and to the weight of the elevator itself, and to this force from the cable, which you could call a tension force. I'm calling it a cable force here. And it would be very important in your doing this problem that you realize that it's being lifted at constant speed. And so, in addition to these 2 forces, your complete free body includes this recognition that there's no acceleration, and then you proceed to do the problem. Here you have you do have acceleration. This is being accelerated forwards by this tugboat, which is also accelerating forwards at the same rate. There's this cable between them. There is the force of the tug on the ocean liner, and there is the equal and opposite force of the ocean liner on the tug. Here's the force of the tug on the water, and the equal and opposite force of the water on the tug. Notice that these 2 are forces on the tug. This force is on the water, and this force is on the ocean liner. And there are other forces that we're not drawing in here. But would you please comment on which one of those is a correct statement? Person pushing a box across the floor, and he's slipping. Would it be to his advantage, because of the friction from this box, would it be to his advantage to push up on the box, or push down on the box, or continue pushing straight forward? Also, if he is struggling to get it going, and then he manages to get it start going, would it be okay for him to stop and start over again, or is there an advantage to him keeping it going once he gets it started going? So your thoughts on that. And similar to that previous problem, here is a box that I've announced that I tend to move the box across the floor, and then I get called out of the classroom, and you, in a sense of mischievousness, decide to make it hard for me to move the box. So I want you to brainstorm, what could you do to the box to make it hard for me to move? And do not include in your list, I really want you to brainstorm on your worksheet, don't include hiding the box or writing "do not move me" on the box, because you know how much I'm given to authority, or burning the box so that I would endanger myself by trying to move it, or covering the box with boogers so that I would be too grossed out to touch it and move it. No, more legitimate ideas. Now you have started the show again, And I hope that you see that your ideas fall into two categories. One would be to make the box push against the floor harder. You would put weight into the box. And the other is to change the interaction. You probably had a much richer collection of ideas there. The interaction between the box and the floor. That you could make the floor rough, or you could make the floor rubberized, or you could glue the box to the floor, you could nail the box to the floor, or you could make a little wall around here so that that was super rough floor. But those are, I'm going to propose, the only two ways to change the frictional interaction between the box and the floor. It turns out that normal force, that is how hard the box pushes down against the floor and hence how hard the floor pushes up on the box, that normal reaction, the friction is proportional to that normal. That if you make the box twice as heavy, then there will be twice as much friction. That written as an equation would be that there was this constant of proportionality, and the name we give to that constant of proportionality is a mu. We call that mu the coefficient of friction. And this is it. This is the formula for frictional force. It depends solely upon the interaction between the box and the floor and the normal force, how hard the box presses against the floor. That this coefficient of friction you would not be able to predict. It is determined empirically. You just put a cardboard box on a concrete floor and you find out what the coefficient of friction is. You put a concrete box on a sheet of glass, you find out what the coefficient of friction is. Put the concrete box on a sheet of steel, you find out what the coefficient, and so on. But there is this value for how much the two interact with one another, and then you have how hard they press together. That is it. That completely determines how much friction there will be. You can see this makes the word fun, so how hard would it be to remember that formula? You find a way. I point out to you that not included in this formula for friction is how big the area is. Turns out friction is independent, much to our surprise, of the area of contact. Why do people put fat tires on their cars then? Indeed. And it is not a matter of how fast the box is going. I don't see velocity in this formula. That does not determine the friction. The last point, which is very important and very hard for people to hear, is that the direction of the friction force is such as to oppose motion. It does not oppose force. It does not oppose acceleration. It opposes motion. Okay, the nature of friction, the reason there is friction, is that in fact these electrical forces that hold the surface together also attach to the other surface. So they weld to one another through these molecular bonds. And when you move it, those welds have to break. And there is where the frictional force comes from. If it is sitting still, then many more of these welds occur, and there is greater friction. If it is sliding along across, then the welds, fewer welds are made, and so there is smaller friction. And as a consequence, we have two different coefficients of friction. Coefficient of friction when it is sliding, and the coefficient of friction when it is sitting still. So motion, the velocity does matter, but once you get it moving, going slowly or going quickly does not matter. Velocity does not appear here in this equation. And then there's this curious, why is that not an equality? Well, consider this scenario. I have a 100 Newton box, that's its weight is 100 newtons, so the normal force on it would be 100 newtons since it's on a horizontal surface. The coefficient of static friction is 0.7. And so if you take 0.7 times the normal of 100, you get that the frictional force is going to be 70 newtons. But suppose this push was only 30 newtons. Well, that's nonsense. Friction does not initiate motion. You're not going to have this box take off and start going backwards to the push. And so what happens is if the push is 30 newtons, the frictional force will just be 30 newtons. If the push is 50 newtons, the frictional force will be 50 newtons. But if the push is 80 newtons, then you've exceeded the maximum value that friction can have. Then the box would bust into the kinetic mode and you would have to have a new coefficient to calculate what the friction would be. And so this is the maximum frictional force would be mu times the normal. But in general, the frictional force is going to be only enough to keep the thing in equilibrium. All right, so here's a problem for you to do. You do it, good for you. Here is another problem that you have these 5 scenarios. Here there is no force except possibly friction. And here you are pushing it, but it's not moving, and so on. Here it's accelerating, here it's not accelerating, here it's accelerating again. Would you please rank these according to the size of the friction force and choose which answer is the correct answer? Finally, a practice problem. And I would like you to just do the practice problem, but at least to the point of setting up the sigma F equations, and you can stop short of doing them. You could do them if you like. That's the end of the show. But I'm going to go ahead and do this problem in case you feel stymied, like it is too much for you. I hope you would make an attempt and then come back and start the show again if you so desire. Okay, so we've started the show again. That you need to free body this. You're going to have weight, and you're going to have the person's pull, and you're going to have the normal force, and you're going to have friction. Friction would act parallel to the ramp, but does it go up the ramp or down the ramp? And you look here and you see it is sliding down. And so friction opposing motion would go up the ramp. Then the question was, what is the box's acceleration? Well, it's definitely going to accelerate parallel to the ramp, but does it accelerate down the ramp or up the ramp? I don't know. You would go ahead and make a guess. It doesn't matter what your guess is. If you guess wrong, then the answer you get will be negative, and you just know it goes the opposite direction to the direction of the arrow you wrote there. It is no biggie. Then what we're going to do is realize that I want to deal with the forces going perpendicular. Since the acceleration is going to be parallel, I need to deal with all the forces going parallel, causing that acceleration. And then I will take the forces perpendicular to that, to the surface, and there would be no acceleration there. So I'm going to have to take this force here and break it into components, parallel and perpendicular. And then I'd have to use the 30 degrees to get of this 70 newtons, how big is that and how big is that? And I will have to take the weight as well and break it into components. And if this is 25, then that angle there is 25, and so I would use sine and cosine of the weight, which would be 980, and get those components. And then I would take, in the perpendicular direction, I have the normal, and I have the component of the pull, and I have the component of the weight, and I would add those all up, and they would add up to 0. And parallel to the ramp, I have the component of the pull, and the component of the weight going in the opposite direction that I would add on, and the component of friction. And I would add those up, and then I would put 100 in for the mass, and then I would solve for the acceleration. There you go. Thank you.